Okay, so this is just some of the problems, and this is the OpenStack textbook for College Physics Volume 3, 3.2, The Mathematics of Interference. So I'm going to go through just some of them. I'm not sure how many I'll get through in one video, but we'll just do some. Maybe I'll do one at a time, so that's a possibility. We'll see how it goes. Some of them are really similar, though, so I might solve like 3 or 4 of them. So, first off, I want to discuss the double slit experiment first. So, in yellow over here, we have this light source, and these are supposed to be just, I don't know, a way to visualize that light is leaving this source and traveling. I know these are awful ways, but just to get the idea that it's traveling this way towards this screen that has 2 slits. One here, one here. They're separated by a distance d. And obviously light's going to go every which way. It'll go this way and what have you. But we're just focusing in on 2 parallel beams of light, if you will, traveling this way to this screen with no slits. So if we were to look at these are just, obviously they're pretty rough waves, but they're waves traveling to this particular spot. And where we have the waves, I've talked about this before, so I don't want to overdo it, but when we have something like this, the peaks match with the peaks, you have constructive interference. When you have something like this, it's destructive interference. So this is constructive, this is destructive. Okay. And we're taking where this second beam of light is at an angle theta off of the horizon. So that's this. It's a little messy, I know, because I was drawing a lot of things, but that's theta. Then we drop a perpendicular here, so that's a right angle. And then I kind of try to blow this triangle up. We have our right angle, our hypotenuse is over here, that's D. Sorry, that's my brother screaming in the background. And if you do a little bit of geometry, you'll find that theta is right there. And right here is lambda. That's your wavelength. So you can see by some right triangle trig that sine of theta equals lambda. Now, for constructive interference, we say, so for constructive, we say d sine theta equals n times lambda, where n could be 0 or 1 or 2 or 3, and it's just this sequence of numbers. Okay, so that's where I try to draw it here, but it obviously it got a little messy. The 2 wavelengths are off by 1 factor. So if you were to increase it by an integer number like 1 or 2 or 3, the wave is going to get caught up with, if you will, each other. So that's constructive interference. For destructive interference, well, we want the opposite. We want it to be off by a factor. So instead, that's an awful theta. There we go. We say 1/2 plus n to guarantee we do not get one of these numbers. Okay? So that's kind of the setup for these problems. Hopefully that kind of makes sense here. We have this light source emitting light. It goes to this slit. And in some places, the lights will meet up. For example, here, I just picked one out of the many, many possibilities. And I picked it such that it's an angle theta off of the horizontal. And then from there, we can do some right triangle stuff to get a relationship between the distance between the slits, the angle, and the wavelength. Sorry, my fan's knocking all this stuff over. So let's see what we have here. Maybe we can do a problem or two. At what angle is the first order maximum for 450 nanometer wavelength blue light falling on double slits separated by 0.0500 millimeters? Okay, and that's for number 16. And they want to know at the angle. Scroll down, please. I'll do this color. Well, we know that d sine theta is equal to n lambda. When they say the first order maximum, that means constructive interference. So this would be a max, and this would be a min. That's what they mean by max and min, first of all. So we know which one we want to use. First order is referring to our n. So first is just going to be 1. And if we want to solve for theta, all you have to do is a little bit of algebra. Divide over by d. Sine theta equals lambda over d. Or theta equals sine inverse lambda over d. And then from there, all you need to do is convert. So I would convert this into nanometers into meters. So you'd multiply that by 10 to the negative 9th to get meters. And then for millimeters, what is it? It's times 10 to the negative 3rd, I think. Cosenta is 2, deci is 1. And then you just convert it, and you'll get your angle. And when I did that, I got an angle of 0.516 degrees. So that is this green angle. Hopefully that makes sense. I spent a little time trying to set up the whole visuals here. If you have this visual kind of down, at least a little bit, I think the rest of it comes pretty easy. It's just playing around with the equations. So I might pick and choose a couple problems that are a little different from the rest and just get you used to how these sort of problems go. But if you can visualize it, I think these problems come kind of easy. So hopefully that